Hello and welcome to another episode from Spiral Physics Education. So in this lesson, well, it's going to be quite mathematical. We're going to be looking at electrical energy using these equations. We're going to be looking at electrical power using these. And really, that's about it. And what will be really helpful for you to get the most out of this is to know what the definition of energy, work and power are. Also the definition of currents, difference between volts and potential difference, and also be very confident with Ohm's law. And if you're not sure about any of those, do check out some of the other videos on the channel to help you get up to speed on those so you can get the most out of this. Okay, so electrical energy. Well, if you remember, the energy is the ability to do work, and well, we need to know what work is. So work is done when energy is transferred from one store to another store. And we need to think about the volts as work done per unit charge. So if we look at work done per unit charge in a little bit more detail, that means volt is work divided by charge. All work is equal to the volt times charge, so W equals VQ. So we've got an equation there for electrical work from the definition of the volt. And we can also see that from the definition of current, Q equals IT. So if we look at that equation, W equals V times Q, where that Q is, I'm going to substitute in Q in the form IT into it. So we also get an equation W equals ITV. Now I usually prefer to put it into ITV because I remember when I was a student, probably younger than you are now, that's how I remember that equation because it was like one of the TV channels. And back then there were only 3 TV channels, so it was easy to remember. So that we've done the equations for electrical energy, we look at electrical power. So we need to know the definition of power. So power is the rate of doing work. So that means power is work divided by time. And work is also voltage times charge from that previous slide that I was looking at. So if this time, where we've got power is work over time, I'm going to substitute in, instead of work, V times Q. So we've got now power equals V times Q over time. And remember that Q equals IT, so I'm going to substitute that in as well. So now I've got, instead of VQ over T, I've got V IT divided by T. And obviously the T's will cancel out. And now that gives me power is current times voltage. Now, if you remember Ohm's law that said V equals IR, well, instead of that V in P equals IV, I'm going to substitute IR into it, which is going to give me P equals I times R, or P equals I squared R. So electrical power equations then, so that's the origins of P equals IV and P equals I squared R. Those are just the origins of those equations. So here's a summary then. Power is work over time. Power is also IV. Power is also I squared R. V equals IR, which is Ohm's law. Q equals IT, which is just the definition of current rearranged. Electrical work is ITV. Electrical work is also V times Q. So there's a summary of all of the equations that we've used so far in this short introductory video. So let's have a look at an example. So in this question, we're going to look at a 12-volt bulb working at normal brightness, which means its potential difference is 12 volts. And we're going to look at a power source supplying 3 amps to it for 10 minutes, and we're going to calculate how much electrical energy is transferred to the bulb from the power source. So most students will go straight for the jugular and stick all those numbers into an equation. However, the exam boards occasionally like to throw in a little bit of a strange curveball. In this case, 10 minutes. We hardly ever use minutes in any calculations. So the first thing to do is convert 10 minutes into seconds by multiplying 10 by 60. We'll get 600 seconds. Now we can select an equation. So work is ITV, and we can substitute in 3 amps, 600 seconds and 12 volts, and we get 21,600 joules of electrical energy supplied. Let's have a look at another example where we've got a 240 volt motor being used to open an automatic door at a supermarket, which I'm sure you've all been through. And let's say that the current being delivered is 12.5 amps, and that when it opens the door it does 4,500 joules of work. We're going to calculate the power of the motor and also how long it takes for the door to open if it does 4,500 joules of work. So let's have a quick look at the units first, just to see if they're trying to put a curveball in. Volts, that's okay. Current, amps, and work, kilojoules. Oh no, work, we don't want work in kilojoules. That's a bit sneaky. So let's convert that into joules first. That's the first thing. That's definitely going to get me a mark in an exam. So let's see if we can work out the power now. So power, well, we've got voltage, we've got potential difference and currents. So we can use that. So power is current times potential difference. Plug in the numbers for those. 3,000 watts, job done. Next part, how long does it take for the door to open? So, well, power is rate of doing work or work over time. I've got work, I've got the power I've just calculated, and I want the time. So I can rearrange that for time, which is work over power, which is 4,500 divided by 3,000, which tells me it takes 1.5 seconds for that door to open. Personally, I'd like it to open a little bit faster than that. All right, so let's have a look at another example, and this is to do with something that you've all probably got in one of your hands right now, or if not, very, very near you. An iPhone. Personally, I'm a Samsung guy, but don't hold that against me. So this is from the iPhone X, I think, information, which is completely up-to-date information if this is 2019 or 2020, and completely retro should it be 2022 or beyond. Anyway, so apparently it has a battery where the information on the battery is 3.7 volts for its EMF or voltage, and that battery has a capacity where it can store 10.8 kilocoulombs of charge when fully charged, and that means apparently that it can play video for non-stop 13 hours before it completely discharges. And what we're going to do is going to calculate, first of all, how much work the battery can do given that information. And we're going to quote it to two significant figures. So let's have a quick look at the units first. We've got voltage, which is fine. Blah, 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 blah. We've got kilocoulombs. No, kilocoulombs. Let's get that sorted out. Let's turn kilocoulombs into coulombs. We do that by multiplying by 1,000. So we've got our charge as 10,800 coulombs on our iPhone battery when it's fully charged. Read through a bit more. Oh, hang on, 13 hours. Hardly ever use hours in our calculations. So let's convert that into not minutes but seconds. So multiply it by 60 and multiply it by 60 again. We get 46,800 seconds of time for our battery use. Okay, now we can get back to the question. So the question, what were we asking? How much work can the battery do? So we've got the definition of the volt is work done per unit charge. That means work is voltage times charge, or potential difference times charge. And now I can put in my 3.7 times 10,800, which gives me 39,960, but it's to two significant figures. So we've got 40,000 joules of work that our battery can do. Job done for that. Next part. We're going to calculate how powerful the phone is and how much current is delivered by the battery when it's playing this video. So how powerful is the phone? So we've got work done, and the work done is done over 13 hours, or specifically 46,800. So we need an equation that links power, work, and time. Power is the rate of doing work. 40,000 divided by 46,800. So good, I put it there twice, which tells us that the power of the battery is, or the iPhone is 0.85 watts. Next thing then is how much current does the iPhone draw from the battery when it's playing the video. So we've got power, we've got voltage, we want current. So trying to link all those together. Let's try using P equals IV. I'm going to rearrange it so that I equals P over V, which means we've got a power of 0.85 watts divided by 3.7 volts. That tells me that the iPhone is going to draw a current of 0.23 amps. So your iPhone draws a current of 0.23 amps for 13 hours, sucking it dry of 10.8 kilocoulombs during that time. And if you can watch videos non-stop for 13 hours on your iPhone, it is better than my Samsung. So, well, I hope you found that useful, looking at lots of different electrical equations. It's quite useful when it comes to improving your understanding of physics and getting those grades boosted. So have a look at it again and other videos on my channel. Don't forget to subscribe, and I'll see you next time on Spiral Physics Education. Goodbye.